Hey, welcome to The Explainer. You ever watch a sprinter just explode from the starting blocks, or a ball arc through the air and wonder, what's really going on there physically? Well, today, we're going to break that all down. We're jumping into kinematics, which is just the science of how stuff moves. So you see someone like Usain Bolt just tear down the track, right? And your brain just goes, whoa, that is fast. But for a physicist, that's just the beginning. What does fast actually mean? Is it really the whole picture? Nope. Not even close. Let's dig in.
So the real question is, how can we take something so awe-inspiring, this amazing feat of human ability, and describe it with the precise language of physics? How do we turn that wow moment into numbers and data we can actually work with and understand?
Okay, let's get into it. And to do that, we've got to start with a word we all use every single day, a word we think we know inside and out: speed. So, in physics terms, speed is simply the rate you cover distance. It's how much ground you cover in a certain amount of time. You just take the total distance you went and divide it by the total time it took you. It's kind of like the trip summary on your car's dashboard, It doesn't care that you were stuck in traffic for 20 minutes and then floored it on the highway. It just gives you the average for the whole trip.
But here's the thing. In physics, just knowing how fast you're going, well, it's often not the full story. I mean, if you're trying to get to a friend's house, telling you to drive at 50 kilometers per hour isn't very helpful, right? You need to know which direction to go. And that little tiny addition, direction, is what elevates speed into something much more useful, what we call velocity. Now, to really wrap your head around velocity, you've got to understand this key difference between two words: distance and displacement. They sound similar, but they're not. Distance is the total path you've traveled. Think of it like the step counter on your phone. It counts every single step, every twist and turn. But displacement? Oh, that's much simpler. It's just the straight line distance from your starting point to your ending point. That's it. It's the as the crow flies measurement. And this is a perfect example. Let's say you start at A, walk all the way over to C, and then double back to point B. Your step counter would be like, great job, you walked 12 meters. That's your distance. But your displacement? Well, you just look at where you started, A, and where you ended, B. You are only 8 meters to the right of where you began, so your displacement is just 8 meters to the right. And that is what gets us back to velocity. See, velocity is just the rate of change of displacement. It's literally speed with a direction bolted on. So the car is going 60 kilometers per hour, that's speed. But the car is going 60 kilometers per hour west, now you're talking velocity. See the difference? It's that simple, but it's absolutely crucial.
But let's be honest, right? In the real world, things almost never move at a perfectly constant velocity. We're always speeding up, slowing down, turning. So how does physics account for all that change?
Well, there's a word for that, and it's acceleration. And listen up, because this is the part where a lot of people get mixed up. We tend to think acceleration just means speeding up. But that's not the whole story. Remember, velocity has two parts: speed and direction. So if you change either of those, you are accelerating. In fact, there are 3 ways you can do it. Okay, first, the one we all know. You can speed up. You're in a car, you hit the gas, you go from 20 meters per second to 30. Yep, that's acceleration. Easy enough. Second, and this is the big one, so really lock this in. You can accelerate just by changing your direction, even if your speed doesn't change one bit. Picture a car driving on a merry-go-round or a traffic circle at a perfectly steady 20 miles per hour. The speedometer needle isn't moving, but because the car's direction is constantly changing, it is absolutely 100% accelerating.
And number 3, you can probably guess this one. You can do both at the same time. You can change your speed and your direction. Think about getting onto a highway on a curved on-ramp. You're turning and speeding up. So the big takeaway here is any change in velocity, speed, direction, or a mix of both, that's acceleration. Period. Okay, so we have our big 3 ideas now: displacement, velocity, and acceleration. These are like the building blocks, right? And with them, we can now start to learn the secret language physicists use to tell the entire story of motion, without ever having to write it out in sentences.
And it all starts with some simple data collection. All you do is track where an object is, its displacement, at different moments in time. You just write it down, and you end up with a straightforward table of numbers, kind of like what you're seeing here. But then, you take those numbers and you plot them on a graph, and boom, all of a sudden, that, let's face it, pretty boring table of data, it magically transforms into a picture, a visual story of that object's journey. And this, my friends,
is the absolute heart of kinematics, the motion graph.
So, what can these graphs actually tell us? What secrets are hiding in the slopes and the lines and the curves? Let's decode them.
First up, let's look at a displacement versus time graph. The key thing to look at here is the steepness of the line, what scientists call the gradient. Just think of it like a hill. The steeper the hill, the faster you're moving. So on this kind of graph, the gradient, or the steepness, literally is the object's velocity.
All right, but now let's switch gears. What if we plot velocity against time? The graph might look kind of similar, but what it's telling us is totally different. Now the steepness of the line, it's not velocity anymore. It tells us how the velocity is changing. And what's the word for a change in velocity? You got it, acceleration.
Check out this example right here. The line is perfectly straight and it's sloping upward. That means its gradient is constant and positive. What that's telling us is that the velocity is increasing, nice and steady, by the exact same amount every single second. And that, folks, is the textbook definition of constant, uniform acceleration.
But wait, there's more. Believe it or not, this graph has another secret hiding in plain sight. And it's not about the line itself. It's about the space underneath the line.
If you actually calculate the area of that shaded shape under the graph, what you're finding is the object's total displacement. It makes sense, right? You're basically multiplying velocity by time. It's an unbelievably useful trick, a super powerful way to figure out how far something has gone just by looking at a graph.
You know, this whole idea of constant acceleration, it's not just some abstract thing on a graph. It actually describes one of the most common and fundamental types of motion we see every day, stuff falling. For centuries, everyone, including brilliant people like Aristotle, thought heavier things fall faster. It seems to make sense, but then Galileo came along and showed that nope, they were all wrong. If you can ignore air resistance, everything from a tiny pebble to a massive cannonball, they all accelerate downwards at the exact same steady rate.
And that really leaves us with a mind-bending thought to end on. The fact that a feather and a cannonball hit the ground at the same time in a vacuum. It seems like a simple party trick, but it's telling us something incredibly deep about gravity and how our universe works. So, what is this one simple fact? That everything accelerates at the same rate no matter what it is. What does that really tell us about the fundamental rules that govern everything around us?